Tonight's speaker, Dr. Kimberly Ennico Smith, is a NASA research astrophysicist at Ames Research Center. She's multidisciplinary in her approach to space instruments, telescopes, and mission concepts. She's designed and built infrared, airborne, and space telescope cameras and spectrometers. She's tested detectors in laboratories and particle accelerators, and designed low-cost suborbital instruments and built lunar payloads. Most recently, she served as deputy project scientist leading the calibration of the New Horizons Pluto flyby mission and project scientist for the Flying Infrared Observatory SOFIA. Studies of our universe through multi-wavelength eyes from telescopes on mountaintops, airplanes, balloons, rockets, and satellites in orbit have revealed a beautiful, mystifying, dynamic, and rather extraordinary place. Our Earth's atmosphere no longer became a limiting filter by using infrared wavelength light for observations. This talk takes us on a local tour of our Milky Way and highlights recent observations of our many infrared eyes on the sky. Will these new observations get us any closer to learning about how our universe works and where we come from? Join me in welcoming Dr. Kimberly Ennico Smith.
Thank you very much for inviting me here. I have some takeaways up here in the front that you can get after. I've got pictures of the universe in the infrared, some stickers, and a nice poster of the electromagnetic spectrum. So, is it possible to lower layers? Well, I am delighted to be speaking with the San Francisco Amateur Astronomy Group. I think amateur is a totally wrong word for a group like this, because you guys know a lot about the universe.
You know what it means, though, in Latin? For the love of.
For the love of, yes.
So we accept that.
Okay. So the talk that I'm going to share with you, and throughout the presentation, I'm going to be revealing a lot of what we're seeing in the universe at these infrared wavelengths. And sometimes, because these are wavelengths our eyes cannot see, the images might look a little different in colors, but the astronomers are choosing the colors to emphasize certain things, and I'll point those out as we go on. What we don't see in the universe might surprise you. For example, what you're seeing on the screen right now is an image of the center of our Milky Way, visible. But at wavelengths longer than our eyes can see, more specifically the infrared, the universe is revealed. You see bubbles, you see pillars, you see gas, dust, things carved by starlight. So by looking at what is revealed in the infrared is telling us a lot more of what's going on in the universe. So I titled it The Infrared Sky Reimagined, because the new data from this fleet of infrared observatories is changing the way we're actually looking at fundamentals in our universe. And there's going to be another fleet of infrared observatories in the future, and I can't wait to see what we'll learn next. So as Linda had introduced myself, I'm usually the person behind building the telescope and building the instruments that take the pictures. I have done some observational astronomy, but I'm usually found in the lab, making sure that the cameras and the spectrometers and the instruments are taking the data that the astronomers will use to study. But of course, this talk is not just about any of my work, it's about work from the entire astronomical community. So seeing our universe in new ways, the infrared sky reimagined. It's an outline, and I wanted to say that this talk could go on for many hours, but I'm going to focus more on the local, because there is a lot more to discuss beyond the Milky Way. I'll start off with a sort of a primer to get us to introduce some terminology that I'll refer to later in the talk. And I have 3 acts to the story of our infrared sky reimagined. And I hope you will agree with me as we go through this presentation that there's also beauty when looking at the universe in the infrared. Astronomers might look at all the nice physics that's going on, the fact that we can see things we couldn't see before, but there's also very beautiful these new images. So what is infrared? This is a familiar image for some of you, but I will take a liberty to introduce some terminology. This is an infographic of the electromagnetic spectrum. This is the definition of light when we parse it out by different wavelengths. You may be familiar with the radio, or the microwaves, or X-rays when you go to the dentist or the hospital. These are all forms of light. We're just separating them out by different types of wavelengths. And of course, what our eyes can see, visible. A part on the slide here, the gray area, is a representation of the transmission of our Earth's atmosphere. This has essentially shaped the way we understand the universe historically. When it's all the way up to the top, that means the atmosphere is blocking light, we're scattering it away. When it goes down to the bottom, you actually can see through the atmosphere. And so we have two windows, the visible window and the radio window. And this is what dominated astronomy for centuries. It was not until we built telescopes on top of mountains, or put them on balloons and airplanes and eventually satellites, that we opened up the spectrum. I'll be focusing on the infrared, where there were these windows that you could glimpse through from the ground, because you have partial good transmission. And with the talk, I'll focus on this range of wavelengths, 1 to 1,000 microns, which is broadly the infrared into the submillimeter, where this is the focus of the science revealed for the universe. Okay? How many of you recognize this part of the sky? So it's the dark markings of the sky. So the sky has a lot of things we cannot see. Unlike the Greek celestial tradition, which focuses on stars, several other cultures, like the Aboriginal astronomers, focus on the dark areas. They're the smoke from the old spirits, or the monsters that live in the dark patches. These are holes in the sky, coining a term from Sir William Herschel, who kept on building bigger and bigger telescopes to kind of tackle the dark markings in the sky. Or it could be Edward Barnard, the 20th century astronomer, who you might be familiar with the Barnard catalog. He went and he photographed, and he opened up this whole area of wide-angle astrophotography. This is an image of the Taurus molecular cloud, and only 400 light years away, but part of several of the catalogs that Barnard would do. So what are these dark patches? There are these molecular clouds. They are stellar nurseries where stars are forming. But why do molecular clouds appear dark? It's because a property of the materials that make up the clouds, dust. So what's happening? The physics behind this is these particles that are a micron in size, at shorter wavelengths of light will be scattering or absorbing that wavelength. Yet at the longer wavelengths, the dust will peer through. And these particles are much smaller than the human hair, very, very small in size. Now, one of the properties of the dust. And here's an example, looking at a Barnard 68, named after the gentleman who did the photography of the sky. And shown on each of the patterns is the wavelength of light. And so the dust is absorbing the shorter wavelengths, but it's allowing the longer wavelengths to pass through. In fact, using the infrared techniques is how firefighters often look through a smoky room, because they're using the property of light that it's passing through small particles. It's allowing it to pass through. Yet, it may sound counterintuitive, but we can also see molecular clouds. This is through a different property of dust, dust emission. So what's happening is the dust is absorbing in the visible, but that's heating up the dust grains. And now it's going to re-emit that light in the infrared. It's almost like a cosmic recycling of light. Let me show you an example of this. Familiar constellation, Orion, taken in the visible. If we had 100 our eyes could see at 100 microns of light, this is what Orion would look like. What is happening is all that sunlight is being absorbed by the dust, which is everywhere, and it's being re-emitted. This is a transformational, because when you look all over the sky, over half of the sunlight, starlight, that has been produced ever since the Big Bang has been absorbed and re-emitted at the far infrared wavelengths. And this means if you're not looking at the universe in the infrared, you're missing out on a lot of information. So this is one way we can see molecular clouds, the dark markings of the sky. A second way is through molecular transitions. So when molecules are rotating, or they're vibrating, or they have an energy transition, that activity is going to release energy. And by doing that, we can then see the light. This is a visible picture of the Horsehead Nebula in Orion. So this would be in Orion's belt, and it's the leftmost star in the belt. There's a nebula you can see off to the lower right. But if we looked at that at the longer wavelengths, in particular transitions of the carbon monoxide molecule, this is what we see. In fact, this is a false color image of 3 different transitions of carbon monoxide. And you can learn about the temperature, the environment of the clouds. So we can see clouds through that dust emission and also through molecular emission. There's a third way we can see molecular clouds. I'm going to introduce a terminology called polarization. Treating light like a wave, it has, if you've gone through electromagnetic theory, a light wave traveling this way has an electric and a magnetic field. It passes through space, but this orientation can change anytime light interacts with anything, whether it scatters or diffracts, refracts, all the different ways that light interactions with things. We may be familiar with our polarized sunglasses. We take advantage of the fact that sunlight scattering off molecules and dust in our own atmosphere preferentially places that light in a certain orientation. We put our polarized sunglasses on to remove light from different directions, and we remove glare. At the longer wavelengths of light, there's an interesting phenomenon going on with these dust grains, which we know are there from the dust emission. In the presence of a magnetic field, these dust grains will align themselves. And when they align themselves, they will polarize the light. So the light might be coming in all different directions, but if you're in the presence of a magnetic field, you'll see a polarized light. And this is something that the Sophia Flying Observatory has been looking at, is the polarization of dust. So the leftmost image is a star formation region, the dust emissions. We can see the cloud. But now we have a different instrument that can exploit another property of light and look at how the light is polarized. And from that, we can infer the presence of magnetic fields. And I'll get to more about magnetic fields as we go on. So to sum up the primer, observing the universe into the infrared is delivering some 4 key fundamentals. We can see into clouds. We can see clouds because they're emitting dust. We can see the molecules that the clouds are made of and understand some properties. And then we're also discerning the presence of magnetic fields, so looking at the polarization of dust grains. Now there's other aspects of studying the universe in the infrared, like redshift. It's another phenomenon that, that is another talk in itself. But I'm not ignoring that, it's just that I'm going to focus on these phenomena. Okay. So, I wish, after learning all this, I wish I could see the universe in the infrared. So I wish I was a superhero that had infrared vision. So there's a cast of characters who have superhero vision that are the infrared. But today's superheroes in the infrared are the suite of amazing tools. We have satellites that have come and gone. We have satellites current in space right now observing the universe in the infrared. We have telescopes on the tops of the driest mountains to work through those pockets in the atmosphere. We have put telescopes on balloons and on airplanes because they can look and peer into the infrared. Those are our infrared superheroes of today. And then James Webb Space Telescope, which will launch in 2 years from now in 2021, is an infrared space telescope. It's cold and 6.5 meters, and that's going to reveal the infrared universe in another way. So, Act 1, Rising of 400 Billion Suns. And this is a photograph that was taken of our Milky Way, and you might recognize certain parts of it. But I'll bring up a quote. Why did I say 400 billion suns? It's actually taken from a poem that Carl Sagan wrote. A still more glorious dawn awaits, not a sunrise, but a galaxy rise, a morning filled with 400 billion suns, the rising of the Milky Way. So the beauty of the universe is inspiring poetry. And I think that maybe, when you look up at the night sky and you go to a dark sky, it is breathtaking, wouldn't you agree? I mean, often as we live in a city, we don't get to see these dark skies. But again, we see them with our eyes, and if we had our infrared telescopes looking at the sky, it would be an amazing light show. So in a little bit some more terminology, I'll use the term light year. The light year is a unit of distance. Light's traveling at a fixed amount of speed, just like we're traveling in a car at 50 miles per hour. In an hour, we have traveled 50 miles. But at the speed of, I can't remember this number, 670,600 miles per hour, in 1 year, it travels 6 trillion miles. So a little bit of orientation is that the molecular clouds I'll be introducing you to and sharing with you are on the order of 400 light years away, or maybe 1,000 light years away. It's sort of nearby, but still several trillions of miles. The whole Milky Way in which we are in is about 100,000 light years across. And we're located about 30,000 light years from the center, about 20 light years above the plane, and tipped about 63 degrees. If I had more time, I would have crafted another talk about how we figured this out, because we actually had some recent information from the WISE satellite that put to rest the long-standing debate whether we had 4 arms or 2 arms. Because this has been going on for centuries, you know. I mean, it's been looking at us like, how can we're inside the Milky Way, how are we supposed to explain what we're all seeing? But we could probably chat about that afterwards. And then I'd like to quote Douglas Adams. Far out in the uncharted backwaters of the unfashionable end of the western spiral arm of the galaxy lies a small, unregarded yellow sun. Now, I'd like to think that our part of the galaxy is pretty dynamic and a bustling place. Yeah, so we are in the western spiral arm, we're in the Orion spur, and yes, we know our location. Okay. This is a projection of the Milky Way. It's called the Hammer projection. And I'll point out, this is in the visible. This is, the Milky Way contains over 200, 300, 400 billion stars. We still don't know how many stars are in our Milky Way. And it has a lot of material to make a lot more. This is a visible image. And so we're tracing that starlight, and you see the dark markings in the sky. I'll point out Orion and the Magellanic Clouds in this projection. This is a photograph taken by Alex Mellinger. It took 3,000 images to put this all together. Now, the visible Milky Way, we launched the satellite in the 1980s called IRAS. And this is what that projection of the Milky Way looks like in the infrared. This became the first all-sky infrared roadmap. So it was a huge discovery mission. Thousands of new objects were discovered. We discovered the infrared cirrus for the first time. Debris disks became part of the nomenclature. We hadn't known they existed until IRAS. We also had determined the spiral nature of our galaxy. This was only not known until the 1980s. And we discovered a whole new class of galaxies called the starburst. It was revolutionary. In fact, that faint S blue curve is actually the emission from our own solar system. So we're seeing the thermal emission of our own solar system. So what I show is I often show the wavelengths in the lower left and the satellite that took the images to kind of piece the story that when you talk about astronomy today, you have so many tools. But looking back at what the visible looked like to the infrared, it's very different. When we go to longer wavelengths, this is by ESA's Planck mission at 350 microns. What we're seeing here is we are seeing the emission of that dust. If you remember that Orion image and seeing that image of all this dust, this is what our Milky Way looks like. You'll notice that it's all over. And it's above and below the galactic plane. And you don't see any stars because you're starting to see just the dust emission. And this is where over half of the light of the universe is emitting. If we went and we looked at a molecular transition like that carbon monoxide, this is what it would look like. And stunning enough, it's all constrained along the plane of our Milky Way. This is where our stars are forming. And they're going to form out of the densest clouds. So it's a very different picture when you look at the universe at different wavelengths. Let's exploit that molecular transition again and look at the universe. This is taken with the COBE satellite. Use a different instrument than the one that found the cosmic microwave background. This is looking in the infrared, looking at ionized carbon. This is a very special line for astronomers because it's extremely bright and has a lot of information. It is 1% of the entire luminosity of the Milky Way is in this line. What is going on there? So understanding what this line is telling us, it's often telling us about a transition between atomic and molecular gas. It's often used now by the submillimeter community who looks at this redshifted into the submillimeter to understand star formation in the most distant of galaxies. But the discovery of the carbon line with the COBE satellite has opened up a whole new area, and I'll touch on C+ later on in the talk. And there was a satellite that was also launched with Planck called the Herschel, and it studied the C+ line. It built an instrument specifically to study that, and it made a discovery. It turns out that we have been underestimating the amount of gas in our own Milky Way by over a third. So the top part is the CO. So the CO is radio followed by submillimeter infrared. This is where astronomers thought this is all the gas that will make the stars in our Milky Way. It turns out there's a lot more information in the C+ line, this ionized carbon line, that carbon can hide in that line, not just in CO, and it is a reservoir for making stars. So the search for C+ with the ESA satellite Herschel transformed our understanding just in the last few years that we hadn't put a bounding on even all the light in our own Milky Way. This is not to say this is anything different from the dark matter, dark energy part. We still are missing a lot of the information in the universe. It just means we're also underestimating what we're seeing with light, because we haven't truly looked at what our Milky Way looks like at all the different wavelengths. So that was one of the big surprises. So I gave you an overview tour of the 400 billion suns, and guess what? There's more than 400 billion suns because there's a lot more material to make suns, and that was one of the discoveries with the Herschel telescope. So Act 2, stars are born. So infrared astronomy focuses a lot on star formation. It's because we can peer into those dark markings on the sky, and we can go into where the molecular clouds are forming stars. And we can also determine makeups and processes by looking at the molecular lines. We can learn about temperatures, pressures. Can anyone spot something familiar? What do you see? You see the Horsehead Nebula off to the right. So this is an infrared image of the cloud from which the Horsehead, you see the peeking out to the right? Very different than a visible image. And this was taken with the Herschel telescope. The green and blue regions are the warmer dust, and the red and orange are the cooler. We're not seeing that many stars, we're just probing the dust. But there's a lot there, there's a lot of beauty in there. But good eyes. So our picture of star formation is mature, but it's far from complete. You know, this is a concept of how we think far simplistic view. We start off with a region of dense cloud of dust, and we call these molecular clouds. They may then denser parts collapse under their own weight, and then they'll first form clumps and cores and stars, and then it collapses in four, maybe forms a disk, and then from disks form planets. But honestly, we have huge unknowns. We don't know what triggers the collapse. I mean, we always thought, oh, you have to have a supernova go off. But what if you're in an environment that doesn't have supernovas? What will trigger the collapse there? How fast does the collapse occur? So we can measure the speed of gas. We can try to understand. There's a lot of big holes to the simplistic. So this is where a lot of focus of modern infrared astronomy is focusing on several century-old problem that we still haven't figured out how stars form. We have an idea, but the devil's in the details. So this is a beautiful picture of our Milky Way in the visible. I'm going to give you a tour of 3 clouds, and these may be clouds that you photograph when you're out at your star parties. So we're going to go to the carbon monoxide map of the molecular clouds, and because that's where the star formation regions. And I'm going to give us a tour of Taurus, Ophiuchus, and Orion, and highlight some recent results looking at understanding what's happening in these three stellar laboratories. Taurus is about 400 light years away. It has stars in isolation. Ophiuchus is about 400 light years away, but it's really densely packed. You can see how the stars interact with each other. And Orion, a bit further away, about 1,300 light years away, but it's got stars of all shapes and sizes, and it's a bit crazy. And we're still learning a lot about it, but if you went to the scene of the crime of Orion, you're still trying to figure out what happened there. So let's start off with Taurus. So I showed this picture earlier, but I had cleverly cropped down the lower right. Who recognizes what's in the lower right? The Pleiades, seven sisters, right. So if you want to look at the Taurus molecular cloud, when the Pleiades is up, you look to the north left. And so what I'm going to also show is the degree on the sky that each of these images are representing. So you can get a feel whether this is something for my binoculars or my wide field telescope, my narrow telescope, for the visible images. Obviously in the infrared you have to put your telescopes in space. Oh, thank you. So this is, a modest sky on the size on the sky, 16 degrees. So it's a nearby laboratory with isolated stars. So 400 light years away. It's spanning about 10 degrees in the sky. But there's not many stars seen, and this is why it's seen very dark. So not many big stars are there to illuminate the clouds. And it has less stars per volume, so this makes this a laboratory to study stars in isolation. What does this region look like at the longer wavelengths? This is an image taken with the Herschel telescope. At infrared telescopes, we can see now the molecular clouds revealed. So let's zoom in on this 14 degrees. So you take a closer look. One of the amazing discoveries of Herschel was that stars are forming in filaments. We had known about filaments before, but Herschel showed they're all over our galaxy and all the molecular clouds. They're very elongated and thin structures. And a curiosity, regardless of their length, their width is about 1/3 of a light year. We figured this out. Could be something to do with stability or how they form. Most of the stars in these molecular clouds with the filaments are in the filaments. Yet there are sometimes filaments with no stars and sometimes stars without filaments, so the model doesn't fit. But are we embarking on a new model of star formation? It's no longer that spherical amount of gas collapsing and forming single stars. Something may be causing these filaments to occur. And why are they forming in filaments? Are the filaments, what causes the filaments to fragment into clumps that will collapse? But we're seeing filaments. And they're just seen in all different colors. So we're having a debate about how we're understanding star formation. So let's zoom in on a region called LINS 1544, named after Dr. Beverly Lins. She's an astronomer who cataloged a lot of these dark nebulae in a Palomar sky survey. And you might be familiar when you're looking at her objects. Anything with an L is named after her. So we'll look at LINS 1544 and zoom in there. And there's a discovery that was made there. We discovered water. We discovered water in a cloud that had not formed a star. This was the first ever detection of the water molecule seen in space that wasn't associated with after a star had been born. It had enough water to fill 1,000 Earths. So water had been seen in molecular clouds since the 1960s, but it hadn't been seen in a place in the universe where stars hadn't been formed. And how do they know that stars hadn't been formed? There's other telltale signatures. And what was also neat is you see with the spectra, I show the x-axis is velocity. Their spectrometer had such a high resolution that they looked at 40 water lines, because it said that the universe is revealed to these molecular transitions. They can actually accurately measure that wavelength so precisely. And they were able to see a Doppler shift. They saw that the water was moving relative to the star. In a sense, it might have actually been a tracer of gravitational collapse. It's a bit more of a speculation, but it was an interesting indication that we can also use molecules to tell us about the speed of things, and perhaps we can look at that timing thing. How quickly do stars form when gas is collapsing? Still don't know that answer. But the detection of water in a place in the universe where stars have not yet been formed, basically told us that water is forming very early on than we had expected to believe. And you didn't have to wait for hydrogen and oxygen to go through a stellar phase in order to be formed. That was interesting. Let's move to our second star cluster, molecular cloud, Ophiuchus. So Ophiuchus is also very nearby. It's about the same distance as Taurus. It's much more denser, and it's located near Scorpius. And so you see Antares, the lower red white light. So if you're ever looking up at the Scorpion and look for Antares, you can look over to the top left again, and on a dark night, spy Ophiuchus. Ophiuchus is a favorite topic of many of my friends who love spending lots of time at telescopes looking at Ophiuchus. And what does Ophiuchus look in the infrared? So here we're going to show what Herschel showed. So again, we have these beautiful wisps of gas and dust and these filamentary structures. Now let's zoom in a little bit further to the innermost 2 degrees. And I'll blow this up, and this is a picture taken with the Spitzer Space Telescope. I haven't introduced Spitzer yet. Spitzer is just running out of its lifetime right now. It was launched in 2003. I built one of the instruments for Spitzer, and this picture is just amazing. The colors are represented as such that the longer wavelengths of light are shown with the redder colors, and they're revealing the cocoons of the younger stars that haven't been formed yet. And the stars that have shedded their cocoons, shedded their placentas, are in blue. And it's so dense that they were able actually to do a statistical study, and they counted the number of what we call pink stars versus blue stars, but they're looking at stars before they shed the cocoon and the stars that had shed their cocoon. And they found an interesting distribution had been very similar. So it was almost as if with mass, so the distribution related to mass. So the interesting thing was, they may have actually, the massive stars form in a similar way than the lower mass stars. This is always another conundrum in astronomy. How do massive stars form? But the fact that we're revealing a whole range of populations. So looking in the infrared, we're peering through that dense nebula, and Spitzer found 400 of these young stellar objects and was able to do the first time statistical study of this part of the star formation series. A neat fun fact, Ophiuchus actually has the host of having the first brown dwarf found there. And so brown dwarfs are low enough on the stellar scale that they can't ignite their own light. But we can see them in the infrared. They have signatures in the infrared. And they're sort of called failed stars, but they're an interesting bridge between stars and exoplanets. So the infrared is also allowing us to do a lot of studies of brown dwarfs. So let's zoom into the middle part here. The Sophia Flying Observatory has this polarimeter on board. I mentioned polarimetry with this orientation of how dust is aligning themselves in the presence of a magnetic field. So with the Sophia instrument taking an image of the polarization of the light of this region in Ophiuchus, found a puzzle. They had found that the grain alignment seemed to change as you go deeper and deeper into the nebula. And this postulated a question. Is it the gas that's shielding, gas from a star that's nearby, is it shielding the radiation and we're seeing something like that? Or are the dust grains themselves changing their shape and their size so they're no longer polarizing light as effectively? Or maybe the magnetic field is doing something we don't expect. Or we're trying to still understand how the magnetic fields affect star formation. So we have a paper just came out actually last week about this result, casting doubt to warn astronomers who are using polarization of grains to infer magnetic fields to be cautious, because there may be other factors at play contaminating the way you're interpreting your results. There could be an influence of what's the radiation environment, or is the grain size changing, or is the magnetic field doing different things. So now we have a less fuzzy idea of how grains align in space. And why do we care about this? If we want to understand how the role magnetic fields help or hinder star formation, the way we study magnetic fields a lot is using polarization of light. If we don't understand what the polarization is telling us, we don't have a handle on how magnetic is. Now you can look at magnetic fields at other wavelengths and learn other properties, but at least in the infrared we have a new mystery to uncover. Okay, let's move on to my last molecular cow, the very famous Orion, and famous constellation in the sky, and the movie will play. And we're going to zoom in onto Orion's sword, which has the Orion Nebula, M42. And this region of the sky is about the size of a full moon, half a degree. And it's a well-studied object. So, I mean, how many of you have seen Orion in your telescopes or taken pictures of it? Yeah. I mean, can you ever get tired of looking at it? Isn't that beautiful? So this is a picture in the visible, and let's move on to that. Oops. Okay. In fact, this was taken with 3.5 hours with a 4-inch telescope, so it's well within, it's a very well photographed object in the sky. And I hope to convey to you that there's a lot of mystery still to be held, and it also has a lot of beauty to it. So Orion is well studied because it has a host of stars. It's got the tiny stars, it's got the massive stars, it's been hit by supernova. Over the last 12 million years, it's given birth to 10,000 stars or so, and dozens of them have exploded. And so we're starting to see a really complex area of active star formation. And there's stars being born today. And so it's a common area that whenever we're working on new techniques or new theories to test, often we go to Orion. Now Orion is pretty far away. It's 1,300 light years away, so much further away, but a lot of the stars are much brighter. So let's look at this region across the wavelengths of the infrared. So this is what our eyes can see. This was taken with a telescope just in the visible with a CCD camera. If we look at it just slightly longer wavelengths, the near infrared, this is taken with an 8-meter telescope, we start to penetrate into the cloud. So if I zoom back between the two, you can start to see there's a lot more stars there, and the nebula looks a little differently. Now this data taken with the 8-meter and the near infrared, it revealed the bubble to the north, and we started to see a lot of these brown dwarfs. And so now we have a different population of studies the star. Now we go from the near infrared to longer wavelengths. What Spitzer looked at, this is what Orion looks like at about 5 microns to 24 microns put together. So we get the discovery there is that you can see the joining between the bottom nebula and the top. See those little pink stars? They discovered new stars being formed on a filament between the two stars, revealed again with the infrared. Now let's even go longer with the Herschel Space Telescope. And that's what Orion looks like. And this is at 70 microns. The stars have disappeared, and we just see the gas. Sophia looked at it as well and focused on that C+ line that I mentioned earlier. This is what the nebula looks like at C+. And now isolating the C+ line at 158 microns, they were able to test some pretty interesting theories in star formation. And a paper came out in January in Nature where they, another thing about studying a single line is you can do this Doppler map. You can look at whether the gas is coming towards you or away from you. And so they were actually studying the motion of the gas of the Veil Nebula, which is the bottommost nebula, and how it was moving and how it was interacting. And they had learned that there was a dearth of stars forming, and it was the stellar winds from a giant OB star that was stopping star formation. So this was changing our paradigm. Up to now, astronomers were saying only supernova explosions are stopping star formation. Now we have to say no. Sometimes massive stars can do the same. So they did a statistical study of the amount of stars that were happening in different parts of the nebula and looked to see, and they were able to actually measure the stellar winds coming off a giant star, and it worked out that stellar winds should not be underrepresented when you're looking at trying to compute how much star formation is going on. Why is this important? When we do lots of studies of any of the galaxies at the edge of our universe, and we're trying to understand their star formation rate so we can understand our star formation, our Milky Way, we often are studying the C+ line, and we're learning that there's a lot more complexity going on from simplistic theories. So these beautiful, the Sophia Flying Observatory has an instrument to measure this line and is going off and studying a bunch of molecular clouds to do exactly these surveys. This has not been done before, looking at the interactions of this particular gas. And we're choosing this one because it's the brightest line. So we have some new theories on star formation and what halts star formation. So that's going back to that beautiful visible universe. Of course, Hubble looked at it. In fact, this is 520 Hubble images stitched together. And the majority of the light you see in the visible is dominated by those 4 trapezium stars that are in the middle of the nebula. And if those stars hadn't been there, it would be quite a boring place to look. So let's zoom in on the inner 10th of a degree. So this whole heart of Orion would have been invisible if not for these 4 stars called the Trapezium Cluster. And their ultraviolet light is illuminating the gas around them. Now we're seeing that light, and we're also seeing the dust that's absorbing it. But what does this look like going forward into the near infrared? So to go from the visible to just short wavelengths. So it's very different field. A lot more stars are revealed. There's a lot more redder, younger stars. And there's this glowing red area. This is also taken in the from the ground at shorter wavelengths, but in the infrared, so we can peer into that. So we have a lot more activity going on that was hidden by the visible. A lot more stars than the Orion. With the polarimeter on Sophia, we now have mapped out the magnetic field of Orion in the infrared. And what's interesting, if your eyes can just see, it looks like an hourglass around the area that looks red in the image. This is a region called the BNKL object. It's a massive star being formed. But the magnetic field lines are indicating that the magnetic fields are playing a significant role in the star formation. What's curious is those magnetic fields are having nothing to do with the trapezium. So if I point those out, this BNKL region is a region of massive star formation. The magnetic fields are in some sort of hourglass, but at the trapezium, they're going right through it. So now we have an ability to see a cloud through a different mechanism, this magnetic field, and try to piece together what may be going on. At longer wavelengths, Orion looks like this. It's that emission of the dust, pointing out those 2 regions again. And this also was a place of a new discovery. The Herschel telescope discovered the oxygen molecule for the first time after a 230-year hunt for it. Atomic oxygen had been seen in the universe, but molecular oxygen, O2, what we breathe, had not been seen. And it's still a mystery. It is actually still quite rare, and they found it in a couple of clouds. But then the spacecraft ran out of cryogen, so we still have a mystery on our hands. I'm waiting for the next infrared space telescope to go out and look for oxygen again. So oxygen is the 3rd most abundant element in the universe after hydrogen and helium. Yet O in the O2 is very rarely found. So when they found it, it was great, but they have this question: why has it been elusive? Why is it 1 molecule of oxygen for every 1,000,000 molecules of hydrogen? It's just a puzzle. We don't know why it's found in Orion. Again, you go to Orion because it's nearby, it's quite bright. There's a lot of interesting places to look at, but they didn't find it everywhere. So that was an interesting discovery. Again, using the molecular to help us see clouds. And Herschel also found pretty much the precursors for life in the Orion Nebula. This is a spectra, and you can identify all the different molecules: carbon monoxide, sulfur dioxide. The infrared is extremely rich in molecules. And the terminology that astronomers like to use when they're looking at Herschel spectra is the weeds and the flowers. The flowers are the things you're trying to find, but the weeds also are very interesting. There are all these extra lines. And so when the James Webb Space Telescope, although it's not in the far infrared, it's more at shorter wavelengths, it's going to have a similar discovery space we're going to be seeing areas of the sky in the infrared and with a spectrum, and we're going to be looking at molecules and looking what things are made out of. So we have a treasure trove. And again, the Herschel Space Telescope, wonderful, the largest infrared telescope we've flown in space, but it ran out of cryogens in 2013. And so we only have that data to mine, so we'll wait for the next one. Okay. I'll segue into my last part of my talk, but I really like this quote from Bill Watterson. If people sat outside and looked at the stars each night, I bet you they'd live a lot differently. So I've taken you on a tour of generically looking at the Milky Way at different wavelengths. Then we zoomed in on 3 molecular clouds, which I hope are areas that you'll look at in the night sky, because they're beautiful and visible even though they're dark, and sometimes they have some colors. But there's still a lot behind those molecular clouds in the infrared. The third part of the talk is to the heart of it all. Let's go to the center of our galaxy. Okay, so a little orientation. This is our Milky Way, and we live inside the spiral galaxy, and we're about 30,000 light years from the galactic center. We can see the galactic center because of the property of light that in the long infrared wavelengths we can peer through the dust to see to the galactic center. So here is a visible image of the Milky Way, just taken with a Nikon camera. 3 10-minute exposures. I'm not sure where he was at the time when he took this. But you see the dark markings in the sky. This is where we'll zoom into this middle area here, and this is where the center of our galaxy is. And you know, a lot of it is hidden. So we'll use the infrared to see through the interstellar smog, as I like to call it. So we're into the heart of the galaxy. An image I showed earlier in the talk, about 8 degrees on the sky. So again, something that your binoculars can see, but we won't be able to see it because this is the infrared. And 3 microns to 24 microns. The blue are the old stars, the green is emission from organic molecules, and the red is more of a thermal emission. There's over 100 million stars in this small patch of sky. And it's much more crowded than expected. So dynamicists who are trying to understand how stars are forming and how galaxies are made, they count stars. And the fact that we had these new glimpses to the center of our galaxy, close in laboratory, 30,000 light years, they're finding that they have to change their models because it's much denser than they originally thought. Let's zoom in further, 5 degrees. And let's look at the same region at the longer wavelengths with the Herschel images, and I'll zoom in on that. This is a very interesting image. So the inner 5 degrees of our galaxy taken at 70 microns, 160 microns, and 350 microns. If your eyes discern something, the left side looks a bit more red than the right side. We have an asymmetry in the center of our galaxy. So the blue is matching the warm gas, the red is the colder. It's usually a standard technique. But 75% of the cold gas is on the left side, the positive longitude of the galaxy. Also, it's going away from us. And the warmer dust, the blue stuff, is coming towards us. So we have to figure out a model to explain the asymmetry of our galaxy. So there's a lot of studies going on to try to understand how can you have this happening, what distorted the gas, why do we have this, the left and the right are looking very different. Another interesting discovery, if you can't quite see it here, but I'll zoom in and highlight it, is Herschel discovered a twisted ring in the inner 200, 300 light years of our galaxy. Can you imagine just a rubber band that's elongated, twisted, and tilted? Is gas, has this form, and they measured the speed of the gas, and actually the speed of the gas was measured in the radio, but they found that it was actually moving at one speed, and it's moving towards us. So now we have a twisted ring, also offset in the other direction, moving towards us. But what's keeping that stable? Is this sort of something a leftover from perhaps an episode in our galaxy a long, long time ago? No one has explained this ring. So there's papers that describe it's there, but there hasn't actually been a reason why we would have a ring of gas 300 light years in diameter, quite narrow, twisted, and moving in one direction. So it's got about 30 million solar masses, which is quite a lot. So let's zoom into this part of the galaxy, so towards our center of our galaxy, and look at even longer wavelengths, peering even deeper, to show what the inner 2 degrees on the sky of the center of our Milky Way looks like. And this is a composite, actually, of the infrared going up to the millimeter and radio, just to show that this area of study is more than just the infrared, because at the longer wavelength you can still peer through. And the relations of the molecular hydrogen, which is shown in the purple, this is the fuel from which stars are forming. So this is a question that we're exploring about how can you make stars in such an extreme environment. Let's zoom in to the innermost half degree, or what we call the central molecular zone, the central 700 light years of our Milky Way. This is a beautiful image taken from 3 space telescopes in the X-ray, Chandra, near-infrared Hubble, and mid-infrared Spitzer. It is the most energetic place in our galaxy. It's like the downtown of a large city. You know, it's crowded, it's active, and it's vibrant. And it's just full of lots of information. And so it becomes this finding map. Let's go to the heart, the innermost degree. So I've just tilted it on its side and zooming in on what is at the center of our Milky Way. It is a radio, it's bright in the radio, and it is a supermassive black hole. Why do we know it's a supermassive black hole? I'll get to that in a moment. And it's got about 4 million solar masses. It's quite small. The black hole that was imaged by the Event Horizon Telescope a few months ago, that is a 6 billion massive solar mass black hole. Still very far away in M87, but our black hole is pretty massive, and it's nearby, which makes it a great laboratory. But to explore it, it's got a supernova remnant. This is about the innermost 25 light years. Zoom in even further. Within the innermost 7 light years, we actually have a ring of dust from which stars could form. And we've now mapped that out in magnetic fields. This was actually presented at an American Astronomical Society meeting last week, showing the magnetic fields 6 to 7 light years from the center of the galaxy, and postulating that the magnetic fields are stopping the material from falling into the black hole, and this possibly could explain why our black hole is not as active. It's not shown to be very active. And if we zoom in beyond the 6 light years to the 3 light years, we see something called the mini spiral. And there are 30 million stars just in that small region. You zoom into the central light year, and there's a surprise there. We don't have many old stars, but we have a lot of new stars. And then let's zoom in even further from the central light year to the innermost 10th of a light year. And this is where we did have a measurement of the mass of our black hole, because we've been monitoring stars orbiting the black hole, applying Kepler's third law, and then measuring the period of rotation and estimating what sort of gravitational effect would have on that, and the majority of the stars. This has been going on since the mid-1990s, and it's become very robust to show us that we have 4 million solar mass of supermassive black hole at the center of our galaxy, all possible with studying the universe at the infrared and longer wavelengths. And just last week, in the innermost 100th of a light year, the ALMA telescope, which is a sub-millimeter telescope, has actually measured accretion onto the black hole. This is measuring hydrogen gas. So these are slightly longer wavelengths than the infrared. But I would say the studies of trying to understand how a black hole works, we're delighted to have this Event Horizon Telescope, which is in the radio, which is using dishes all over the Earth, so using the Earth as a telescope, and gave us that image of the first image of a black hole, and is also is going to image our black hole. When we get that data, and we show this other data that we've been collecting with these other telescopes, perhaps we might have some pretty good observational evidence of how black holes work and accretion. You know, right now it's theoretical and mathematical, but now we have observational evidence. But there's a lot of interest in that. Okay. So let's sum up the talk. So I was describing our amazing fleet of observatories. I was mentioning a lot of words, Spitzer, Herschel, Planck, Sophia. These are our modern superheroes. They have that infrared vision to look at our local universe. And so don't ignore the infrared. There's a lot of information in the infrared. We discovered recently that we have been totally underestimating the amount of gas in our own Milky Way. Filaments. Filaments are everywhere. Is filaments now the new paradigm for star formation, or a strong subset of that? Water now, we've discovered that water exists before the stars form. That has implications on how we understand water chemistry. Grain alignment is probably more complicated, but this is the first time astronomers have gotten observational evidence to test their theories. So right now it's the battle between the observational astronomer and the theoretical astronomer, because the theoretical astronomer had dominated the field all these years because there's lack of observational evidence. Now we have observational evidence, and now the theorists have a play day. We have an example that stellar winds actually have the capability of stopping star formations. That needs to be incorporated into our models. Magnetic fields are controlling massive star formation. Found molecular oxygen. There's a weird twisted ring at the center of our galaxy. And it's possible magnetic fields are stopping, or maybe an explanation why our supermassive black hole, the center of our own Milky Way, is not so active. Now there's a lot more that I couldn't touch on. I just wanted to give you a flavor of some pretty cool results just in the last few years as we look at the universe in the infrared. And the future is bright. So Stephen Hawking has a wonderful quote: look up at the stars and not down at your feet. Try to make sense of what you see and wonder about what makes the universe exist. Be curious. I think when we all look up at the night sky, there is a lot more that our eyes can't see, but you're still curious about, you know, why does the universe look the way it does? And I'm very excited with the new infrared eyes on the ground. James Webb will be launching in a couple of years. Gusto is a balloon that will launch in a couple of years and will also study the universe in this ionized carbon. Speaking on origins, our infrared telescopes under study right now, and they may fly in the 2030s. These will pick up where Herschel and Spitzer left off, because both Herschel and Spitzer didn't get to really study the whole universe. There's a lot more mysteries, and I'm sure there'll be someone speaking in front of another group about the mysteries of the infrared universe reimagined again with that new data. Thank you.
Box that you had, the Veil Nebula expanding, was that real, or is that an artist's conception? Or
That's real data.
well, how, over what period of time was that?
What is shown is that's the speed. So it was taken over a couple of years, so it's not real-time speed. What you're seeing is the motion of the gas.
Over a couple of years, they got that much expansion?
Yes.
Wow. This was
So when you look at the universe, it's dynamic.
Wow, very much so.
I want to ask you this. It looked as if new stars were forming out of carbon, or some carbon particles, dioxide, or whatever. I thought to have a new star would be formed out of hydrogen, not carbon.
Well, the question about whether new stars are forming there's other molecules before hydrogen. So the stars are forming from hydrogen, but they're in an environment that's enriched by other atoms that were created by stars that have come before. So oftentimes you're looking at a nursery of stars that is not the very first stars, but stars that are the millionth generation, and they're forming in an environment where it's rich in other atoms and molecules.
Are these carbon atoms going to fuse and do the same things? that hydrogen does?
Yes, so there's there's a type of star called the carbon star, which has a lot of carbon in it. And they form from fusion because carbon is higher and they have to wait for the hydrogen helium to fuse and form heavier elements. And so carbon stars, or what we call asymptotic giant branch stars, AGB stars, rich in carbon, are also studied a lot in the infrared because that's telling us about the transition when a star is about to die. And so we're often looking at the envelopes of stars in carbon, but they come from the fusion. Yes. Yes.
You take a picture of a black hole. Wouldn't it just be like taking a picture of a black field?
That's a very good question. So the picture of a black hole, how did you take it? So that you saw the image of the donut that was in the news a couple of months ago. So that's an image taken in the radio. And what they were looking at is the edge of the black hole, so the event horizon for which the light was no longer escaping. So they were still illustrating but it's the measurement of, I forget what the molecule that they studied, I think it was hydrogen, that they actually were able to see where that was in relation to the black hole.
So you weren't actually looking at a black hole, you're just looking at some around it. I assume that we...
That's right.
You were looking at a black hole, but I thought that just this once it might actually be black hole.
So it's still black, but in this event horizon that was measured for the very first time, the fact that it was symmetrical and not offset actually confirmed Einstein's theories. It took 100 years to have this theory, and it was, it's confirmed a lot about what we think mathematically. So the study of black holes right now is going to go through an evolution, because we're going to move from the theoretical only to now an observational base. So this was one of many.
I've also heard about this, I think it's really theoretical, but I've heard about this thing people are talking about. It's called a white hole. I've heard it's similar to a quasar. What exactly is it?
A white hole. Actually, I don't know what that is. So it could be a theoretical manifestation of it. It might have a lot more energy.
I've heard it's basically like a quasar. Do you know what that is?
Well, a quasar is a quasi-stellar object. It is an extremely energetic black hole in a galaxy far, far away, and we had been discovered because it had looked like a star, but it has the properties of being a black hole at the center of a massive galaxy. Yes, and they're all over the universe too, not the local universe, the distant universe. Thank you. Oh, yes, sir.
Hi, yes. Following up on this gentleman's question, you mentioned earlier that there's basically a galactic level of gas and dust, and it just doesn't make sense that all that gas and dust could have been formed through stellar explosions. Is there a theory like where this gas and dust came from, and also, is there any estimate on how much intergalactic gas and dust there is?
So the question is about, could the gas and dust come from other than stars, and then there's an intergalactic dust. Well, there is intergalactic dust. In fact, there is some studies of some, it wasn't in this talk, but looking at dusty galaxies and measuring the flow of galactic flow coming out of it. So there is an intergalactic medium. So there's an interesting hypothesis out there whether that could also seed to be the formation of material for stars. There is a mystery when you go really back in time. How did you form the first stars? And the first stars, and then looking at when did the first dust form? Because you're going to make this jump that you need the first stars to generate the higher element, the carbon, the oxygen, the nitrogen, these things that eventually are going to be dust. Dust is just a particle that's made out of silicate or carbon. But you needed to have stars first to make the dust. So the interesting thing is we see dust much earlier than we see the evidence of the first stars, but we know that can't be true. So we have a chicken and egg problem in modern astrophysics. There's a telescope called the WFIRST, which will follow the James Webb Space Telescope that was going to be looking a lot at that problem. So we might have an answer.
Okay.
But it is a conundrum. I mean, how do you know? When you look at these stellar nurseries, astronomers have a difficult time because you have to take the environment into account. And so if you can find a molecular cloud that doesn't have much going on, it helps you to look at things in isolation, but you still might not getting the real picture. So, yeah.
like some early galactic primeval pretense to a brown dwarf.
Yeah, well, very similar, but the current theory is the earliest stars were actually not the brown dwarfs, but these giant stars, because only hydrogen was around. And hydrogen being the lightest atom is not gravitationally bound, so they're very puffy stars, but they don't live very long. And so then they'll collapse and they'll fall to helium, and then we'll start having the generation of stars. So the thought is the first generation of stars looked really weird. They were big, and they lived live fast, died young, you know. They had a very violent, but we haven't actually really seen the very first stars. And that's an area of soup. But think about, how did you make the first stars? You got to make it out of something, and then what would cause the first stars? And then that would cause a cascade, and then it complicates. Do you need the first stars to, involve why we see all this complexity in star formation? This is why star formation is far from being solved, and that simplistic picture is far from answering these questions. But yes, you're on the right track. I don't know about the chicken and the egg.
That's the way most people think of it for the origins of life stuff. So.
Yeah, are we in the right time, in the right place, with the right amount? Yeah.
Universe, so just the origins of different things.
Yeah. Yeah.
First.
And I have some handouts to take away, some pictures of the first molecule found in the universe, magnetic fields, supernova, and electromagnetic poster for your room, and some stickers too. Oh,
This is from 2005.
wonderful.
This is from 2005.
Oh, wonderful.
Spitzer.
A Spitzer.